So let's continue our journey into the image compression. The next few lectures will be a little bit more advanced. We won't have any specific homeworks on them, but please try to take in as much as you can in the class. Be participative, have discussions around it and everything. Okay. Cool. Let's get started. So just a quick recap, like what is an image, right? So you have an array of pixels, which is like this height, width, and channels. And typically you'll store like each of these values as like 1 byte or sometimes 10 bits or 12 bits, right? And then we looked at like what happens when you do image compression. So it has been, I guess, a long week's break. So I'm just gonna reproduce the slides from the last time just so that you guys can refresh what we saw. So this is a raw image, and this takes like 1.1 megabyte uncompressed. And if you compress it using JPEG by 40x, so this file becomes like 27 kilobytes. And if I go back and forth, you don't really see any difference. So lossy image compression with JPEG seems to be doing fine. But now, like we have studied about the rate distortion, so you can ask the question like what happens if I keep compressing it further and further. So if you compress it further, at this point you can start seeing some noticeable artifacts in the image. So this file is at 14 KB at this point, but you can see quite a high distortion, so as to say, right? And if you go even further, if you try to compress this to like by 2 orders of magnitude 8 kilobytes, now this picture is completely unrecognizable. And then we saw last class that, and we learned a lot about JPEG, like how JPEG exactly works. But then towards the end, we also just briefly touched upon like why JPEG is like, there are many places where JPEG can be improved. Like JPEG is not really our upper bound, so as to say, in terms of performance. And we learned something about of a compressor called BPG. What BPG does is just allows you to have variable block sizes as well as predictive coding. And we had a quiz question on predictive coding just to get you guys practiced. Like I said, it's nothing tough, just like very obvious steps. And so if you compare the performance of JPEG with BPG, so now both of them are at 8 kilobytes, but as you can see, like, as you can see, there's like a big difference in the reconstructed image, right? So obviously, like JPEG can be improved by quite a lot. It's very obvious. But BPG still uses like a lot of hand-tuned parameters, and we'll come to that in a second. And that's what today's lecture is going to be about, like how can you go even beyond like the traditional image compressors. So with this revision, just to go over like the quiz questions quickly. So the first question was just like trying to understand like the same basic principles. I would say just go over the solution in your free time. It's like quite straightforward. The answers for the first 3, it's just like literally doing this width times height times number of bytes math, but now we added an alpha channel to make things more sort of interesting. And then the last question was somewhat interesting, which is like in this question we saw that PMG still seems to perform better than even if you were using just 1 bit for color and 1 bit for alpha channel, which seems like the best you can do in this case. And the question asked like why? And we didn't really talk about PNG in the class. The idea was to, now you know about JPEG, and it was to guess how you can do even better, sort of, why this lossless compressor is performing so much better. And there are lots of correct answers, but the just basic idea what we were looking for, or anything is fine, is that PNG basically does much better entropy coding than JPEG. Recall, JPEG was just doing like a basic run length encoding plus Huffman encoding, but we know that you can do better. And in this case, it's like a really, really uniform image. So PNG, which uses actually an LZ77 based lossless entropy coder, can perform very well because it gets you a lot of matches. So if you look back to your homework 3 Pokemon question, right? So that's really the intuition. It's the same intuition at play here. Okay. Any questions? Cool. And then in the second question, we made this JP274G compressor, right? And the idea was really to work through some of the design decisions, like what we talked about in the class. The first question was around like, when would you think increasing the block size kind of gives you the more benefit? And the main intuition there is that when you have the same image, right, and you are representing it in much higher resolution, that means you have more number of pixels representing the same information, and hence there is lesser correlation between neighboring pixels, right? And so when you expand the block size, you will be able to capture more correlation between pixels within a block size. And that's how like DCT works, and it really helps you. And so the answer for the first one basically like you'll expect to see more benefits for the image which has higher resolution as you increase the block size. And then the second question was now on like, okay, the first question, the idea was like what happens within a block, right? We were trying to see how the correlations work out within a block. The second question was like, okay, now we said that this compressor also uses prediction of blocks based on previously encoded blocks. So now instead of just looking at pixels within a block, we are trying to see if the neighboring blocks and everything, are they predictive of the next block? And again, the idea really is if you can do a better prediction, then you can use that prediction to have lower residuals and compress your stream much better, right? This is exactly sort of the two ideas which BPG also uses to improve upon JPEG, like, right? So it allows you to have bigger block sizes, and it also allows you to have prediction. And so the idea there really was that, if you have more homogeneous blocks, if your image is really consisting of very similar looking blocks, you can do better predictive coding, right? Because it's probably just a copy paste. So in this Charizard image, you'll probably have blocks which are basically all same color versus this assorted Pokemon image which has like lots of things happening. Okay? So this is basically sort of again the ideas of how BPG improves in some sense compared to JPEG. Any questions? Okay, cool. And then the third question was around predictive coding. So we described an algorithm for predictive coding. In class, I just mentioned that we'll do predictive coding is not that hard. So if you work through this question, you hopefully understand the algorithm for doing predictive coding. And then we gave just like two questions, one on decoding and one on finding the errors. And I think it's quite straightforward. But if you didn't understand, just go through this and reach out to us in the office hour or using it. Okay. Cool. Any questions in the so far on image compression or quizzes? No? Okay, great. So let's continue. Okay, again, JPEG at 8 kilobytes. This is the reconstructed image which you get. BPG at 8 kilobytes, super better than what JPEG is. But if you look at it carefully, like you still see some artifacts, right? Like you see some blockiness in this nose. Similarly here, some ringing stuff, right? So this is what you get with ML-based image compression, again at 8 kilobytes. Okay, same file size. And so if I go back and forth between BPG and this, can you see the difference? So it's quite, maybe if you look at the girl's eye, I think. Oops, sorry. Right? So it's quite drastic, right? So the point really is, okay, BPG is also not the same, like it's not really an upper bound. You can still perform much better. And again, if you have to really take a stark contrast, this is what JPEG reconstruction looks at, same file size, versus this is what an ML-based reconstruction looks. So there's clearly a lot of room for improvement. Okay, and so today we'll be learning more about how do you like employ ML and deploy it for the use of image compression particularly. Okay, so just a reminder, this is what a pipeline for the JPEG looked like, and we have seen similar things over past few classes, so now you should be comfortable with the ideas. You start with something RGB, you do color treatment, this is mostly to decorrelate the natural signals, and then we do I would say a vanilla lossy compressor pipeline, which is first you do some transform to decorrelate your components, then you do quantization, finally you do some lossless encoding, some entropy coding, and that gives you your JPEG file, right? And we went into details of each of these components last lecture. So now the question is like, how can we improve this even further? Okay, so the first idea really is like, maybe we can go beyond linear transform. So if you if you saw like JPEG, JPEG 2000, BPG, all of these uses some variants of discrete cosine transform, discrete wavelet transform, discrete Fourier transform, but all of these transforms are just linear maps. It's a matrix multiplication. Maybe we can do something better if we allow for some nonlinear transform coding to take place, which we haven't studied in class at all so far, right? And so this is really the idea. So think of these plots as the two-dimensional vector coding which we have looked at. So x-axis is just some source dimension 1. Y-axis is the source dimension 2. So like x1, x2 things which we have been looking at. These purple dots are the codebook vectors and the regions are the codebook boundaries. And let's say your density function, the actual source which you are encoding, is in this banana kind of shape where yellow color means higher probability density and blue color means less probability density. And so if you were to vector quantize this block and you are only allowed to do like linear boundaries with this vector transform, this is probably the best you can do, right, to capture this. But if you were allowed nonlinear boundaries, then I can exactly cover this this banana peel kind of shape, and I only need to transmit these few vectors, right? And you can be much more efficient. Only these few codebook vectors, yes, right? And so in this very trivial, like a synthetic example, you can already see that, right? Like if your PDF of real sources, nobody said they have to follow some linear boundaries or they can be linearly decorrelated. Maybe there is some nonlinear transform which decorrelates them. So that's one. The other idea is really more related to ML, which is, so in JPEG, we saw there were like lots of these hand-determined heuristics, right? Like we had these quantization matrices, which just came out of nowhere. These were like specific numbers. When I say nowhere, it isn't really nowhere. We motivated it based on NLG and lots of psycho-visual experiments. But nobody said like these quantization matrix is the best one for your image or your particular data set. Similarly, there were like other design decisions like 8x8 block size, why not more, for example. And so there were lots of heuristics involved during the design of JPEG. A lot of smart people really over the years fine-tune each small knob to optimize every bit which contributes and goes into JPEG, right? But this is really hard, right? Also, like if we think about RD optimization, which we actually didn't talk about much, but somehow we have to do this, we have to trade off rate with distortion, and the way you do it in JPEG is by changing your quantization matrix, right? And again, like this change also. So not only the values which were determined for one particular rate distortion, but the change between different rates and distortion, the trade-offs between rate and distortions were also hand determined, right? And there is no way really to know that it's optimal. And so one question really is, can we motivate this decision in a more end-to-end fashion? When I say end-to-end fashion, like in some way to determine to determine our compressor algorithms or the exact weights, depending on like the final value of the rate distortion, somehow figure that out backwards. And if you know ML, you know what I mean by really end-to-end, right? Like, so the whole premise of ML is like, you try to do this end-to-end learning, for whatever you are trying to optimize. And so these are basically, I would say, the two main motivation and ideas for learned compression. Like learned compression just means using machine learning, and it goes beyond all these traditional compressors by going beyond, first of all, linear to nonlinear transform, and then also doing this end-to-end training. And there has been like a ton of work, I would say, in just past one of the early papers by Todorichi in CVPR 15 and Theus in iClear 17, like those were like sort of the first papers which started using ML for compression. But since then there have been like lots and lots of work. Basically, it's a really hot field. A lot of people are contributing, and hopefully by the end of this lecture, I can convince you that it's a really important topic to learn if you want to continue in compression and keep contributing. At least you should know about the techniques and ideas. It's also very interesting because there is a whole CLIC challenge. It's called Challenge on Learned Image Compression, which is, I think, in its 4th or 5th iteration now. And this is happening at Data Compression Conference. And this is a really active channel. A lot of industry, a lot of people, a lot of academia participate in this to come up with the best compressors for images and videos, right? So if after this class, I hope you should also be prepared if you would like to participate in challenges like this. Okay. So another point which I want to make, like lots and lots of interesting works and ideas. We'll only focus on the basic ideas, like the fundamentals. And then you can go on and in future read whichever of these papers you want to build on them. Cool, everyone with me? Excited? Okay, so before I go into learned image compression, since we decided we'll not assume any background, next few slides might be boring for people who are already aware about ML. But if you don't know anything about ML, just hear through the next 5 minutes and hopefully you should have everything which you need to know for at least appreciating today's lecture with regards to compression. But if you already know it, don't worry about it. So this is really 101, 1,000 feet review, right? There are lots and lots of interesting classes which you can take, which will teach you in much more depth, and I'll encourage you guys to do that. But there are three main components to any ML pipeline, really. The first is data, right? So you try to figure out, you try to optimize some problem based on the data which you have been given. The second is some nonlinear model and differentiable architectures, which is this f of x, which is a predictor basically on your data. So you can think of x as your data inputs and y as your labels. Let's look at some examples. For example, your x can be images, y can be whether it is a dog or cat or not. So y can be a binary label per image saying, okay, whether there is a dog in this image or not, right? So your nonlinear model or your function f is basically trying to learn, it's trying to predict whether there is a cat or not in your image. So it's a function of the input data x image, and typically it is a parameterizable model. What that means is it typically it's defined based on some parameters theta. The standard notation for this is something like this. All that means is like, okay, if you recall a rate distortion water filling formula, there also we had a theta, right? Like which was a parameter to parameterize like a rate distortion curve. Think of theta in the same way. Basically your function f is just depends on parameter theta and it takes input x. Okay. The output of this is y hat. Now your y hat can be involved, like, but for now think of it as what your model thinks is the label for this particular image. Okay. So maybe based on whatever model I have, when I input a particular image, it thinks it's a cat, and it was indeed a cat. Or maybe it says it's dog, even though the input image is cat. So it's figuring out based on this, whatever function f on data and parameters to get this prediction, y hat. And this is really the second main component of our pipeline. And the final main one is the loss function. So you need to determine like, okay, so if my model predicts some cat or dog, whether it's correct or not, right? So if given an image, my model predicts cat, one of the loss functions could really be just one hot, right? So you can just decide if it's an indicator, right? So if the predicted value is cat, whether it is indeed cat or not, given the original input label y. Okay, so very, very high level overview. Mostly all of you are already aware of this in today's world and age, but let's start from here. Okay. And then the way this ML pipeline really works is your f can be anything, right? It's just a nonlinear differentiable architecture. It could be 1,000 different things. But the basic idea is you use backpropagation or gradients to actually learn the model parameters theta. And that's what's called training or learning, right? And that happens based on like whatever given data you have, like x and y. The way this progresses is by taking gradients of your loss function with respect to theta. Okay. So here, all I have done is like, remember a loss was just, it tells you whether you were correct or not with respect to the label which was given to you based on the predicted label. Here I have just replaced my predicted label by fx of theta, which is what that prediction really is. And what you want to do is you want to minimize this loss function. So this is an optimization problem. You want to figure out parameters theta which basically minimizes your loss. So you want to train your model or parameter so that your overall objective function reduces, which is this loss function. And the way you reduce this, so this is a general optimization problem. So if you know about convex optimization and non-convex optimization, this is like maybe easy to solve, maybe hard to solve. Typically in our modern day machine learning and world, it's typically a non-convex optimization problem. And so it's really hard to solve this problem exactly. But what you can do is you can do a vanilla gradient descent. What that means is that you update the parameters theta at each time step by taking a gradient with respect to theta of this loss function. Okay? And you keep doing this repeatedly, and that basically updates your parameter theta and gets it to a point so as this optimization function is really, this objective function is really optimized. So you are minimizing the loss, or you are basically finding a model F, which is giving you the correct labels Y. Okay? So if you are seeing this for the first time, are you with me? Is there any questions? Are there any questions? So this is like the basic training architecture, like what you are really trying to do. All you are trying to do is you are trying to find a model which takes an input, some data X, outputs a prediction label Y hat. The way you are trying to find you are trying to find out this model is, instead of maybe doing DFT, DCT, blah blah blah, some hand-driven model, you are trying to learn this model using the data which you have. The way you learn it is you need to define this loss function, which basically tells you difference between the actual labels. So is it actually cat or not versus predicted labels, which is what your model is saying. And then you backpropagate it or optimize this loss function by passing gradients through the network. And that updates your model parameter theta, eventually leading in reduction of this loss function. Okay, and so again, like there are a lot of, I'm trying to summarize this in 5 minutes, like a lot of details, and like, I'm not sure if it's helpful or not, but there are like a lot of classes which goes into much more details. Do check it. But this is basically the summary at the very least, which you need to understand and appreciate to kind of understand today's class. So the first thing is, in ML, you use data to learn the model parameters for optimizing a loss. So these are the three things which we wanted to optimize, like three main components which are there in your machine learning pipeline. You do this by taking gradients of your loss function with respect to theta. And your loss is now, it depends on the theta, because your prediction depends on the theta. Okay? And the main advantage it provides over like just non-learned models is really it allows optimizing essentially any objective function loss, as long as your function is differentiable. Okay? What that means is, so as to be able to do these gradients, you should be able to take this, your loss should be differentiable. And that typically means like if your F consists of multiple layers, you should be able to differentiate through them. It's basic application of chain rule. And again, I know, like, go check out this if you are not following it completely. If you don't know about it, trust me on this. You need the layers to be differentiable so as to be able to do any learning. What that means for us is that it doesn't play well with discrete distributions, right? So our whole lossless compression has worked with some discrete distributions. And so you can't just like go and backpropagate or fit in a standard machine learning model and get a learned compressor, because you have to somehow deal with the discreteness part of the entropy coder. The second main advantage is that it allows you stacking of these non-linear layers. So your model F need not be linear anymore. Okay? What is a linear model? It's basically multiplication. It's just a matrix, right? Matrix multiplication. And if you think about it like stacking of linear layers, so going back to your linear algebra again, stacking of linear layers is basically not so powerful. Because if you were multiplying 3 or 4 or whatever number of matrices together, you could just represent this as a single matrix, right? So like if you had A, B, C, whatever stacked matrix, it still gives you can represent it as a single matrix. So it's not really giving you any more expressivity in your model. Whereas if you have nonlinear layers and then you stack them, then this is no longer true. And that's really the second main benefit of this ML. That's why if you have ever heard of, deep neural nets and like we went from billion parameters to million parameters to billion parameters to 100 million parameters. And the way we do it is keep on increasing the depth and we need more data. All of these are like very punchlines you keep hearing outside. All of them have basically got to do with like this idea that in machine learning, in linear case, there is no advantage of like stacking linear layers, but in a non-linear case, there is like a lot of advantage of like stacking linear layers. Non-linear layers. Cool. Any questions? So this is just like an overview of a standard ML pipeline. Finally, this is the last thing which we need for today's lecture. Again, you don't have to worry if you haven't seen this before. But there is another architecture called autoencoder architecture. And the idea really is that you have some input X. So this is the same input. Okay. This whole thing, you can think of it as your model, So I was saying, so now the last thing which you need to know to appreciate today's lecture from ML is this like idea from autoencoder architecture, which is really, so now you have some input X. You can think of this encoder-decoder pair as your model, and that outputs your sort of Y or X dash here, which is the reconstructed input. Okay, so the main idea here really is that, so in our typical pipeline, we also needed the true labels, so whether it's a cat or not, right? But the idea of this autoencoder architecture really is you try to recover an output which is similar as the input. Okay, and then your loss function can be determined such that you basically want your X dash to be similar to X. So your loss function can be over X and X dash. So you can think you start with an image, you make it go through some architecture, which we'll come to in a second. This is your fx of, in this case, theta phi, which are the parameters. And then the output is just X dash. And then your loss function will be over some X and X dash. So you start with an image, you recover an image, right? The way you do it is that your model actually has a very specific architecture where you first have an encoder which reduces the dimension of your input to something small, this bottleneck Z, and then using that bottleneck Z, you try to decompress it. So you have something which tries to increase the number of parameters and bring it back to the image. Okay? Does this architecture remind you of something? Like hint is right there. Look at the words with respect to Z. Okay, come on. Yeah. So like this is exactly in some, not exactly, but this is in some sense very similar to compression problem, right? So what you are trying to do is you are forcing your network to learn an encoder and a decoder pair. So these parameters phi and theta, such that whatever this low dimensional bottleneck is, which is typically called the latent variables, you are able to recover an image from that or X dash from that, which looks very similar to the original input. This is exactly what we want in some sense in compression, right? Like what JPEG does is you start with that input images, X, you want some low dimensional bit stream, or not actually, there is no low dimensional, no continuous thing there. But you basically want to represent this image in terms of as few number of bits as possible, which is like your bottleneck. And then you start with that bottleneck, like few bits, and try to recover back an image which looks very similar to the original one. Okay, so this is a very popular architecture called autoencoder architecture, and again there are tens of fundamentals variants of it, and then hundreds of more variants on top of each of these tens of variants. So it's a very, very popular architecture. But the idea really is you are trying to learn parameters such that you compress, so as to say whatever original input you start with, and then you decompress to get back something which is original, and you do try to learn this in an end-to-end fashion. You determine a loss over this X and X dash. Cool. Everyone with me? Huh? So now let's get into our, again, like the image compression problem. So same thing what we looked at, but now in words and terminologies which we understand and how we have looked into this problem. So let's say you have some target image like these cats. What you want to do is you want to encode it. That's your encoder to some bit stream. And then using this bit stream, you want to decode it and get some target reconstruction like I had. And the goal really is to do this RD optimization, right? So you want to minimize the distortion between original image and the reconstructed image, given some constraint on the rate. So which is just the length of this bit should be less than equals to B. Okay, so this is what you really want to achieve at the end of the day. And so in traditional image codecs, like essentially the encoding was working in 3 steps, right? So we first did DCT, and earlier we called this symbol something else, but for this talk, let's call it Z. And the reason is we're gonna correlate it back to these latent variables. It's a very commonly used symbol Z for it. So first step was DCT, to decorrelate. The second step is quantization, right? So this is where the loss gets introduced, like loss of precision. And then you would do some arithmetic encoding on these discrete symbols, let's say, or your favorite lossless entropy coder for that purpose. For this talk, let's assume you do arithmetic encoding. The idea you do arithmetic encoding is now you can assume that your length of bits is approximately equal to log 1 over P of Z hat. And again, like we have looked into this through many homeworks and classes, so I am hopeful like now, okay, this idea is really deep down you guys understand it. Okay. And so then what happens on the decoder side, you start with this bits, you do decoding, which basically gives you these discretized latent variables Z hat. And now you do directly inverse DCT transform, right? So this was where the loss was introduced, right? IDCT and DCT were completely reversible transform. And this gives you this target reconstruction. So now the question is, like, how can you improve this, right? So the first idea was, okay, we don't really need these linear transforms, right? Like, no, like here we were doing DCT and IDCT, and we justified it, saying that, okay, DCT is energy segregation in a similar way as we would expect in natural signals, right? But after that, we had some different quantization method and so on and so forth. We are not limited to the linear transform. So let's try to learn something general. Instead of doing DCT and IDCT, let's try to learn some of these, let's try to learn non-linear transforms for doing this image compression, right? And that basically just means replacing this DCT and IDCT with deep, let's say, feed-forward networks or any network for that sort. Don't worry about the architecture for most part of this talk. We are not going to get into much of the ML details, but rather stick to the fundamental concepts. Okay? And the idea really is that if you use these deep feed-forward networks, we should still get this energy segregation, right? Like, otherwise there is no benefit of really doing that. And how do you ensure you do that? So you need to determine some loss function, really, right? Like, so how do you try to figure out what these parameters should be in our ML pipeline? We need to determine some loss function. So one obvious loss function is like, which is what we started out to do, is the rate distortion loss function, right? So what we want to do is we want to minimize rate. And so this is just the Lagrangian formulation. So lambda is just a positive constant. So when you are trying to optimize 2 variables, you can use this lambda to trade off rate with distortion. So one thing you want to minimize is this distortion between I and I hat. The other thing you want to minimize is this length of bit stream in the middle, right? Correct? Okay. And but we know that we can approximate the bit stream length by this log 1 over P of Z hat. Okay. So this is one very obvious loss function which we can use to train this network back using backpropagating and using gradients. Okay. So one way to think about this is, instead of directly doing arithmetic coding, what we need in our pipeline is this probability model, really, right? So you need to know what this P of Z hat is, so as to be able to train this network. Okay. So anyone wants to point out what is an issue with this pipeline? Like, So we have defined this. If I just backpropagate on this loss function, take gradients with respect to this loss functions, can we just learn the END? Anyone who's familiar with ML or what we just talked about, like, so for learning, what do you really need? You need your objective function to be differentiable, right? Is this whole pipeline differentiable? Can I, when I compute the gradients with respect to my parameters, I'll have to compute it all the way backwards. Can somebody point some issues? Yeah?
Getting the probability distribution involves quantizing first, and quantizing isn't going to be differentiable.
Yeah, okay. So as one of the students answered, getting the probability distribution, we first have to get this z hat, right? There is a quantization step in the middle, but I can't really take, I can't do differentiation across the quantization because that's a discrete variable. So discrete operation, I can't really do that. That's correct. Anything else? Is there any other operation which you think you can't backpropagate or take gradients across? So let's say instead of this z hat, I had z. For a second, assume there was no quantization step. I just had log 1 over, actually, no. Let's say you had quantization step. So the other issue is you also have to take gradients across the probability model, right? So one issue is obviously quantization, as the student pointed out, right? Like how do you take gradients across sort of this layer? But the other issue is also like how do you take gradients across your log 1 over probability of z hat? This is a discrete, right? So this is what you are, what you were entropy coding losslessly. So both of these layers, actually you can't backpropagate through it. So that basically stops you from learning end to end. And so there are some simple workarounds. Let's look at both of them. So for quantizer, let's say our quantizer is just simple rounding for now. So that's like a scalar quantizer. I just rounded to nearest integer. So the way people work on it is like during training, you model the quantizer as if you are adding some independent noise, which is like uniform in minus 0.5 to 0.5. Okay, so basically your 2.3 is going to 2, 3.7 is going to 4. Let me just model it as adding a noise which is plus minus 0.5. And now this operation becomes differentiable, right? What that basically means is when you are differentiating through this, you straight away, like your d of z of hat is going to be d of z. So you have something called a straight through estimator. So you behave as if this quantization layer didn't even exist. Okay. While taking forward pass, while you are actually calculating the parameters, you model it as by adding noise. But while taking gradients and updating your parameters, you assume you are not doing anything. And again, this is an assumption. Like there's no proof to it. This is just an assumption. And it seems to work extremely good empirically. That's what has been observed. And this is like actually trick number 1 for dealing with, I guess, quantization steps anywhere or whenever you deal with anything discrete. You sort of model it as some continuous variable z plus some noise added. And in terms of gradients, you just do a straight through estimator, which just means you assume that layer doesn't exist. It's just identity. Okay. So that solves issue 1. But we have a bigger issue at hand, which is I also don't know how to compute this gradient, right? Like gradient of probability of z hat with respect to z hat. Remember, z hat is discrete, right? So this probability distribution is really a table, right? So for each z hat, I have sub p of z hat. And how do you differentiate back through this table? And so people in the field came with a, I would say, neat workaround. Again, it's a workaround and it's an assumption, which is you can parameterize your model P of Z hat using a density function. So this is a bit tricky, and you're like, why we are doing this, and again, all of that, but let's just try to understand what we are trying to do that. So this probability model is in my hands, okay? I want to assume that it is Gaussian, okay? So I'll assume my P of Z hat is Gaussian, P of Z is Gaussian, but it isn't really continuous variable, it's a discrete variable. So one assumption is, like, I can write my P of Z hat as if it's the cumulative density function of a Gaussian, normal 0, 1, at Z hat plus 0.5 minus whatever it is as Z hat minus 0.5. Okay? So it's a trick. Like, let me say I gave this to you, that I could have chosen my probability distribution to be anything. This is what I'm choosing it to be. So my probability of discrete symbol Z hat, I'm saying, is function of this cumulative density function of Z hat plus 0.5 and Z hat minus 0.5. Remember, my Z hat was just a rounding function, so plus minus 0.5, it's the only integer around that, right? But now, since I have assumed this, okay, I can now take the derivative of P of Z hat with respect to Z hat, right? Because my cumulative density function is differentiable. And so, I'll just come back to this plot in a second, but if you take the gradient now of this function with respect to Z hat, that's just the PDF of Z hat plus 0.5 minus PDF of Z hat minus 0.5. Okay? And what I'm showing here is the solid curve is basically the Gaussian PDF, right? And the dots are the Gaussian CDF at Z hat plus 0.5 and Gaussian CDF at Z hat minus 0.5. So as you can see, like, dots are roughly mimicking a Gaussian distribution. So what assumption or what you forced your model, your probability model to be, is such that your discrete variables approximately come across like your Gaussian, as if they had the Gaussian probability distribution function. Okay, this is a bit tricky. Is everybody following what happened here? Have a question? Yeah.
Is the reason that you can do this because you're going to be learning what the Z hat is anyway, and
exactly.
Just learn it with the Gaussian?
Yep. So that's a great question, and that's an excellent question. I was going to come to it right here, actually. Okay. The reason I could assume that my probability model looks something like Gaussian, I could have actually assumed it anything, is because at the end of the day, I'm going to train my parameters based on this log function, right? And my log function has this log 1 over P of Z hat. So it's going to try and produce Z hat, which tries to minimize my log P of Z hat, which, if you recall, gets minimized if my Z hat, the actual produced empirical symbols, follow the same distribution as the model distribution, right? So if you remember the KL divergence idea, you'll have to go back maybe 10 lectures now, but we have kept on seeing this, right? So you are assuming that my parameters, I'm going to compress my discrete distribution Z hat, assuming it has this probability distribution, which is Gaussian of this and this. Okay? If my produced quantized latent variable Z hat don't have that distribution, then the value of log 1 over P will be higher. Right? So that's basically saying I'm compressing a stream, assuming some other distribution than what it is actually coming from. Okay? So when you try to optimize this loss function, when you try to minimize this loss function by trying to learn the parameters of encoder and decoder, the parameters will tune themselves such that the actual output value of Z hat starts mimicking whatever distribution I chose out to be. Okay? So that's why that workaround is okay. You could have chosen anything. You should have asked, like, oh, Pulkit, why are we doing Gaussian? Why not, I don't know, Laplacian, exponential, gamma, zeta, beta, whatever your favorite distribution really is, binomial Bernoulli. It's just because it's easier to track Gaussian. And as we'll see, like, we'll probably just touch upon it. Like, you can do better. So here, it's not even just Gaussian, which we assumed. We actually assumed a normal 0, 1. What this is saying is each of my discrete symbols, which I'm outputting, are IID, not just IID. They have mean 0 and variance 1. You can clearly see I can improve on this even before I say anything else, right? Like, you could probably play with the mean and variance have different mean and variance for each latent variable. But for now, let's assume that. Okay, this is the distribution, and then my learned parameters for encoder and decoder will adjust themselves so that you get this distribution. And once you have this, now you have this architecture, and now you can train it back, like all the way from I hat to I. Every place you can take the gradient at each operation. Okay. Next, we are going to look at, let me just 1 second. Okay. Next, we are going to go through a notebook where we'll do a live demo of running through all of these operations. We're going to train a very simple machine learning compressor for images and see how it goes. But before I do that, I'll actually do this again in the notebook. I really want, so this idea is a bit tricky, like what we discussed. And for me to really see that we have understood this, let me ask you a few questions. Let's discuss a few questions, okay? Let's assume I didn't have this term in the loss function. I didn't care about the distortion, okay? This doesn't exist. Now I try to learn my encoder and decoder with a loss function which is just log 1 over p of z hat. And my p of z hat is defined as the CDF of zf plus 0.5 minus this for a normal variable. Okay. What do you expect my z hats would be? So do people understand the question? I don't have any distortion term in my loss function. I'm only trying to minimize this. And then I'm trying to learn the parameters of E, which is equivalent to saying I'm trying to figure out what my z hat should look like. Right? So let me just try to minimize this thing, log 1 over p. And so what do you think my z hats would look like if I try to learn such an encoder-decoder pair? It's fine. Any thoughts which are coming to your head? So you want to minimize log 1 over p, which is equivalent to what? Maximizing your p of z hat, right? When is p of z hat maximized? It's like a Gaussian. It's Gaussian like latent variables, right? So when is p of z hat maximized? Exactly, like, let's make it like, so when z hat is 0, at that point you have the maximum probability. You have a probability distribution model which assumes maximum probability for z hat equals to 0, right? So if I didn't have this distortion term, and I just try to minimize this log 1 over p, and if I do a good job at minimizing this, all of my z hats will look like zeros, right? But now you know that's a very bad, what's the issue? Why don't I do that always? In practice, why don't I always do that?
You lose all information.
Exactly. So as one student answer, like if z hat is always 0, you'll lose all the information. That's like transmitting maybe something like just the DC value, right? So if all your variables z hat are 0, your decoder can't really do anything. It has nothing to go on forward with, right? So at that point, it's like completely lossy. You are basically sending a static value. Okay? And so why doesn't our machine learning model actually do that? Okay. Again, so the incentive really here for our machine learning compressor is to spread out z hat, right? So if I just keep my z hat at the exact same 0, I'm doomed, right? Like my rate would be 0. I don't have to transmit anything. The reconstructor can just recover 0, but it will get a completely lossy image, right? So I have to spread out. I have to give other symbols z hat so that my decoder can do something meaningful. And this term in the loss function is basically ensuring that you do that, right? So there is also a penalty you pay based on the distortion between image and image hat, right? So if you had a non-zero lambda, if this term exists, you are trading off. You are not really reducing just the one term. Reducing this term would try to push everything towards 0, but this term would say, no, no, no. My distortion loss will become very high. And so I wouldn't really want to do that. So essentially, based on this value of lambda, whatever it might be, you are trying to figure out how should I trade off my rate with distortion, really. Okay? Is this point clear? This is probably one of the confusing points of what's happening. So let me just summarize again. What we did in this whole pipeline is there were two issues. A, my quantizer was a discrete operation. Second, I had a basically table over which I was optimizing, right? Like log 1 over p of z hat is a table. The way we work around this, workaround 1 was okay. For quantizer, I can just do a straight through backward pass, and while forward, I can just add some noise. For my probability table, I said I'll assume some distribution, which I can backpropagate from. And then my encoder decoder will try to output z hats, which have roughly similar distribution. And the way we do this trade-off is by this rate and distortion term automatically figures out this trade-off on like how much z hat you want to be spread versus concentrated. Okay? So, any questions? Otherwise, let's just, so this notebook will post on the website. It's also on the lecture slide, but let's just do a live demo of Lund compression. While I'm starting to run this, it will take a little bit. So anyone has any questions so far? Do we understand the basic idea? Yeah.
We could also optimize over how we are quantizing, right?
Yes. So that's actually, yes, we can. But we are not doing that. So there are various ways you can do that. I'm not sure what you have in your mind. Do you mean like various discrete options for quantization? Yeah, you can now bring reinforcement learning, do all that. Actually, some of the recent works, that's what they have done, like there is mu0. So there they, for example, tried to introduce some reinforcement learning to do rate distortion sort of trade-off. And the idea was not change the quantization, but roughly like that, where you were playing with different losses, discrete loss options, and then you figure out which discrete loss option to pick. Because another way you can think of it is like, it's actually very interesting. There are lots of things you can play with because, okay, one idea could be you have images which is consisting of various blocks. Why am I quantizing it using the same quantization matrix, right? Maybe I can do different rate distortion trade-off per block, and overall that will give me a better image because, okay, some blocks are just consistent, others have a lot of different things happening, so I can do that smartly. I think that was one part of what they did. And you can play a lots of such tricks, but it becomes as, if you have experience with RL, it becomes very computationally intensive very fast. But yeah, that's a fair idea too. Okay, any other questions? No? Cool. So then let's go over this notebook. So here we are gonna build a Lund compressor for MNIST digits. So this is just an example from the data set. And we are gonna do exactly what we talked about in the class. We'll just go over each cell. So first we make this encoder and decoder transform. Sometimes these encoder and decoder transforms are also called analysis and synthesis transforms. The idea is this is like, the idea is this encoder is like doing some analysis over the image and giving you this latence, and your decoder is doing synthesis of the image from these bottleneck layers. So this is just another term for the same layers. Here all we are doing is like, so again, if you've done machine learning, you would appreciate it. If not, it's okay. Just we are gonna show it in live code. So here you are just defining your analysis and synthesis transform as some layers using Keras. So our analysis transform is just some convolutional layers. Don't worry about it if you haven't heard of it. If you have heard of it, that's what we have. And then we have some non-linearities, which are leaky ReLU in our case. And so what this analysis transform needs to do, though, is start from the size of image and finally give you some latent dimensions number of vectors, which is hopefully much more small in number than the image dimensions. That's the really important thing. And then your synthesis transform starts with a dimension which is roughly of like this latent dimension, and then does like upsampling in our case. So that's being done through this cont2D transpose in our case. And that's basically the architecture for your analysis and synthesis transform. So you can also look at what these layers look like. Again, so you have some output shape, some number of parameters. Similarly for synthesis transform, you have that. So in our case, we have a total of 1 million trainable parameters. So you are tuning 1 million different values. Theta is 1 million dimensional, okay, which you are going to be tuning based on this data, trying to optimize for rate distortion. Then we do some like standard image stuff, which if you have started working on homework 4, you would have seen similar transform. You need to be careful about how you are treating images. Okay, so here let's just look at what an untrained network looks like. So right now we haven't done any training. We just pre-process the image. We apply the analysis transform to get this Y. And then we use this Y to get X tilde. So this is like our autoencoder kind of step, right? Exactly that. And then we optimize for L1 loss. You can do L2 loss. You can do many different things. That's not the point of this lecture, but let's say we work with L1 loss. And so this is what your original image looks like, and this is what your reconstructed look like. Like no surprises. Right now we haven't really trained this. We just have some random values for this encoder decoder. Like why would you even expect the X hat to come out to be same? Okay. Now, what we are going to do is we are going to define a loss function. Okay. So remember, so we have to determine some log 1 over P of Z hat. That was our estimated rate loss. And the way we did it was like some prior distribution Z hat plus 0.5 minus prior distribution CDF Z hat minus 0.5. So this function. So go home and look at it. I'm not going to do each line, but basically we are doing exactly same what we have discussed in this notebook. Nothing more fancier. Our MNIST compression trainer basically now takes care of these 2 workarounds during training, which we talked about. So now we first pre-process the image. Then we do this analysis, transform, or encoding. Then we add noise, right? So this is to take care of the quantization step. And your Y tilde, which is an approximation of your compressed latence, is just Y plus noise. And then your second workaround was this figuring out log 1 over P of Z hat, right? So, your workaround 1 was just adding some noise. This is exactly what this step does. You just added some uniform random noise. And then your workaround 2 was to represent your probability distribution as this CDFA minus B, right? And this is what our estimated rate loss is actually doing, right? It's basically just computing probability as differentiation of 2 CDFs, and then it's computing the negative log probability. Okay. And this basically gives you the rate loss. And then you can also find the X tilde, recovered X, reconstructed X, right? Which is just the synthesis transform over your approximation of quantized variables, which is again, so you got the Z hat after adding noise, which is Y hat in the notebook. Sorry, we should have kept the notation same. And then from the Z hat, you can apply the synthesis transform to recover the original image I hat. This is what this step does. And your final loss basically consists of both the rate loss and the distortion loss. And our distortion loss is just original image X minus X tilde. Okay. And so now we can just see if this works. We can apply this trainer to something to get some values of rate distortion. And so in the next step, let's just go ahead and train it, Let's just like backpropagate our variables, take gradients, try to learn these million parameters, which optimizes for rate distortion. Here I'm taking lambda to be 2000 and my latent dimensions to be just 50. Okay, so MNIST is a data set with 28 by 28 images. So from 28 by 28 dimension variable, we are just converting into some 50 dimension variable. And so it's training live, so you can see. So something which you see is that overall loss is going down, which is a good sign. So we want the loss to reduce at each of these iteration. So that's good. But if you see, I don't know, let's say rate loss. If you see rate loss actually increased first, right? But that's not a right, because we are not just optimizing for rate, we are optimizing for rate plus lambda d, and for this particular value of lambda, I might be trading off my rate and distortion. I'm more focused on maybe distortion from the starting point than the initial point. We are basically trading off both these. Okay, so this is training live. So let it finish. We'll just take a minute more. So while it finishes, so what's the next step, right? So this is all of this we did for training, correct? But after we have actually trained, we'll just go back and apply a normal pipeline, right? Which is this. So we'll have the encoder, we'll quantize it, we'll have some z hat, we'll assume it has this probability distribution p of z hat, and actually use an arithmetic encoder. So all of this was to find the weights, encoder, decoder, but finally our compressor needs to come back and actually use some lossless, a real lossless compressor, right? And so that's exactly what we are gonna do next. So at this point, yeah, so we are just running it for 15 epochs, not doing anything fancy. It's finished running. So the next step is basically to actually implement my compressor. And my compressor here, we basically use the AEC compressor. So if you looked into the code from homework 3, I guess problem 4, you probably know what this is. But even otherwise, we have looked at arithmetic entropy coder. So this is just the implementation from SCL. So this is a context adaptive encoder, but here we are not really adapting the context. We are just looking at the encoder from the image, okay? So now let's use an actual compressor and see the performance. So now we can define some encoder and decoder and use this to actually encode and decode images. So the first thing which you see is like, okay, this is what the frequency dictionary looks like when you actually encoded some images from what do I want to say? Yeah, so this is your actual frequency dictionary from the empirically encoded images. So this is the actual distribution of z hat which you got when you worked with this encoder and decoder, right? And there should be a plot below, I think. Let's see, where is that? Okay. Sorry, I think I might have removed it in the end. Okay, never mind. So basically, if you look at this plot, right? Now you can see this has roughly what we expected to see, right? Like, so 0, most of the output latent variables, z hat, actually peaked at 0. And then you have this fall down kind of criteria. So basically here, this is what the actual my p of z hat looks like. Okay, and it roughly looks like what we might have hoped to be Gaussian. The second thing which you see is that if you look at the final rate and estimated rate, they are very close. So final rate is when you actually apply an entropy encoder on whatever discrete symbols you got. Your estimated rate is just the log 1 over p of z hat, where we had an assumed probability model, right? So this is a good sign. It basically says again, like, our arithmetic encoder is doing the right job. Like, it's roughly compressing things to actually you can be more rigorous about this. We know that an arithmetic entropy coder stays within 2 bits of overhead. And if you look at this final rate and estimated rate, you would see like, okay, they are always almost within 2 bits. right? So, okay, our arithmetic encoder did the correct job. And so at this point, okay, we can actually look at the reconstructed images and what the original images are. So on the left here, what we are showing is the original image X, and on the right is the reconstructed image X hat using this learned compressor. Okay, and so for example here, just using 89 bits, you start with this 5 and you get this reconstruction 5. And so overall, this compressor doesn't look bad. We literally class right now, and it's doing somewhat reasonable job. These are again 28 by 28, so quite 900 dimensional images like bits, and black and white, so just 28 by 28, which is roughly like 900 bits, something like approximately 90 bits. We have come up with a learned compressor which reconstructs most like the original. So pretty cool, right? And we didn't have to worry about like figuring out all the designing all the hand-tuned parameters for this particular one. We figured out the exact transform. You didn't have to know about, oh, there exists something called DCT and so on and so forth. If you had this technology and everything before, you would have probably rediscovered DCT using something like this. So that's pretty cool. So the next thing which I just want to show you, oh yeah, so here is the plot. Okay, I thought I had it above, sorry. Okay, so this is again the same plot which we kind of looked at in the lecture, right? So this thing, but just to show you guys again, here the blue curve is the standard normal PDF, okay? The red is basically the quantized PDF values. So this is like what your model suggests. So this is just the CDF of z hat plus 0.5 and z hat minus 0.5, okay? So the red points are same as the blue dots here. This is what we expect our model to be. And green is actually the empirical probabilities. So remember this z hat table which I was showing you for different values of z hat. This is like exactly these values, green ones. So you can see the green is not exactly same as red, but it's roughly following the red kind of architecture, right? And so it's roughly Gaussian. And there is a trade-off between what distortion and all those things, which will actually determine the empirical distribution compared to actual. The final thing which I want to show is this, like if you increase the lambda, okay, this is interesting. So what do you think happens when you increase the lambda? So how do you actually do the rate distortion trade-off, right? So we have trained a compressor. Actually, this is a one tricky point about the ML-based compressors or learned compressors. So we have trained a compressors which work really well for a given value of lambda. It trades off rate and distortion very well when I fixed what should be my trade-off. But you can imagine if I change my value of lambda, my learned weights will be different and they might value rate more or distortion more, which is something, a knob which we always want in lossy compression, right? So in our case, it's lambda. So let's say here, earlier the curves were with lambda 2000. Now let's say I reduce lambda to 500 and I am optimizing for rate plus lambda times distortion. What do you expect? Do you expect your reconstructions to be more lossy or less lossy? Okay, I hear more lossy. How many of you think it's going to be more lossy? How many of you think it's going to be less lossy? Cool. I think everyone almost said more lossy and some people are probably not sure. Yes, exactly. It's going to be more lossy, right? Because now you are putting less weight to distortion. You are reducing lambda. So in your loss function, you are putting less weight to distortion. So you are in essence saying, okay, I'm fine with giving me more distortion, but reduce my rate. Maybe I'm in a really network constrained thing, constrained environment, reduce my rate. I'm okay with taking more distortion. And so this exactly, oops, I had actually trained it. Now I'm retraining it. But this is gonna train and this is exactly what we are going to see. While it trains, let me just come back here and talk a little bit about what are some of the benefits and issues with this learned compressor, and then we'll come back and I'll show you that part. So couple of advantages. First, there is no hand tuning of parameters. You can learn the parameters. What that means is you adaptivity, which was not possible with traditional codecs, right? Your traditional codecs always had the same matrices. But now you can have, for example, custom codec for each domain. You can have like something for cartoons, something for games, something for TV series, and you can figure out different transform code values for each of them, which performs better for that particular kind of data. You can have something content aware or even task aware. So you basically get the flexibility because now you can train these end-to-end learned compressors for a specific task. The second idea is you get a better distortion model separation, which is basically says that here, my distortion could have been anything, right? As long as it's differentiable. What that means is that, so if you recall, long time back, we talked about human vision and we said MSE is not the right thing. Guess what? Like we trained something right now which was optimized for L1. I could have easily optimized for L2, but nobody is stopping us at L2 or L1. We could have basically plugged in any differentiable distortion metric, which even maybe maps human vision better or like human perception better. And actually a lot of work has gone into this, and we'll try to touch a little bit on that in the next lecture. Right? So you can basically completely replace distortion. Remember, this is very hard to do it in the traditional codecs because a lot of hand design decisions were made assuming you are optimizing for MSE or PSNR. Right? So these are like really the main benefits of the learned image compressor. And let's just go back and see whether this finished or not. Oh, it actually finished. And now you see like reconstructions. If you look at number of bits, you get much fewer bits. Like for each of them, you're approximately getting 40 bits. So it indeed reduced the rate. But now you can see like the quality sort of deteriorated at some places, right? So like if I look at 8 and 5 here, and they were still bad, but it's better. Yeah. Another thing you see is that like these ML-based compressors, they are doing a lot of low-pass filtering, like smoothing, which is somewhat, again, we expect because it's hard to encode the high-frequency components generally, right? Okay. So last thing which I just want to cover today is, so what are some of the issues? And even actually before that, okay, never mind. Okay, sorry. Let's just look at this. Yeah. So this is just a benchmark of how these compressors perform in real life. So this is a paper from 2022. Here, different colors are different compressors. The x-axis is bits per pixel, so higher value of x-axis is higher rate. The y-axis is PSNR or MSSIM. Don't worry about them. These are just some metrics. Here, these are quality metrics instead of loss metrics. So higher value is better. And what you see here is like this brown curve is JPEG, this guy here. Okay. This pink one is BPG, pink dashed one. So this BPG, it's this guy. Okay. And there is this something called VVC VTM, which is one of the, I would say, state-of-the-art traditional codec, which is actually sitting somewhere here. I don't know if you can see it clearly. Can you? Like, let's see, this dash brown. Okay. And this is like really state-of-the-art. Even includes some like MLS components in the middle for like some small decision making. But this is not an end-to-end learned image compressor. Still traditional in the sense that still have all the traditional blocks, just uses something to learn a specific block. Versus the blue one, which you see, is what their work is, which is a learned image compressor. And you can see like in PSNR, basically it's on the most on the top left, which is what you want. You want higher quality at lower bit rate. So it's performing best. So what I'm trying to highlight is that these learned image compressors are really state of the art. Like this VVC, has almost spanned 5 to 10 years of research over various components and blocks and everything and like big teams. And then now you have learned compressor which just comes and beats it. No more that optimization. So it's really cool from that perspective that given the amount of effort, the output you can get is really crazy. And this is just PSNR. MSSIM is some other metric which is known to correlate better with human vision. And there the gap is even higher, right? So here you see like BPG gives you a lot of benefit, this guy gives you a little bit more, and so on and so forth. A lot of these traditional codecs are optimized for PSNR, which is like MSE, just MSE in dB scale. But MSSIM, which is also, by the way, a lot of these codecs still look into, even though it's a perceptual metric, a lot of these codecs have still tried to optimize for this, not JPEG. So you can see like JPEG it's very far away. It's like this guy and all of these guys versus this blue guy is like really beating. So there's a lot of promise. So not only you can have these domain aware things, it's really at the forefront. It's state of the art. Okay. So everything is green. Why isn't there a ML based compressor everywhere? Why do we still study it like first 17 or whatever lectures of this class? Why didn't we start with this? One of the main issues with ML based encoder decoders is speed. Really, so now you have to train this, for example, in a simple example, million parameters. Whereas in DCT or in compression in general, I think really one point which we hope we have driven home is that complexity is a really big thing. Like it really makes or breaks whether something is practical, whether something will be used or not, whether something will be deployed. Because these are like ubiquitous operations, they are just running all the time. You need something efficient which can run at speed, right? So this is just like a screenshot from George Todorici's talk at CVPR 20. And what it shows here is like H266 plus enhancement is again one of the more advanced traditional codec, which is still more computationally intensive than JPEG. But this is what ML based codecs were using back then, which was like almost 20x more computational complexity. So now you can imagine, right? Like what does 20x more mean? On the surface, it just feels like, it's 20, right? But no, it's like if something was taking you 1 hour to encode, decode, now it's going to take 20 hours. Something was taking you 1 minute, it's going to take 20 minutes. Now think you are working on your computer and you say, oh, this thing, 1 minute, I'll wait, this will decompress. Instead of that, now if you have to wait 20 minutes, will you use that technology? It's hard to justify that. So speed has really been one of the areas where a lot of work goes into. Don't have to worry about this. But even though this is a blocker, I think one thing which we should really take into account is that machine learning, deep neural networks have really taken world by the storm. And compression is not the only application, right? Like there are tons and tons and tons of application on your phone or your devices to apply this, right? So a lot of work has been really going on into like hardware support for neural net. And now you can think if you have hardware support for neural nets, then you can deploy all of this much more efficiently and faster on any devices you want. And this is happening not only for compression, but to enable tons of applications which are out there, right? So this is happening anyways, and our compressors can take advantage of this sort of hardware lottery or hardware boom in this area. By the way, we have been talking about this. We are not going to touch this in the class. I don't think any team has picked up a project this time around this, but a lot of these image and video compressors, which we talked about, even traditional image and video compressors, actually have hardware support in your computers. What that means is Intel makes chip so that you can decode your images or videos efficiently on the hardware. If you were just using a commodity hardware, you wouldn't be able to actually achieve the speeds which you would like. And again, what this speeds means is whether you're gonna watch YouTube or not, whether that circle of death on YouTube or Netflix or whatever it is, whether it's going to be 1 second or whether it's going to be 1 minute. So a lot of effort goes into that. And so this is a problem which is there even in traditional compressors, but already a lot of investment and work has gone into it. And hopefully in neural nets also, we are gonna see the same. And yeah, so this is like a huge AI chip landscape, like thousands, not thousands, but like hundreds of companies working to make things better. Qualcomm, okay, this is a little bit older numbers, but basically Qualcomm has a recent chip which does extremely efficient ML inference. Today we have M3, I think, Apple chips which are doing the same. NVIDIA chips are coming out for basically doing much more efficient compression, decompression for learned stuff on GPUs. So a lot of stuff is happening in this field. So even though this is a problem right now, it's probably going to be resolved. And the second issue really is just determinism, which is Something to be careful about is like different hardwares might have different floating point operation implementations, and that could lead to just catastrophic failures. Like CPU world has really come together. I think GPU world is still coming together. Every NVIDIA update, you have to be careful and what devices you are working with. So this is like really, even though this doesn't sound big, this is really important when you are working with this ML image based coders. Like whatever you are doing should be reproducible across machines and platforms. Otherwise, again, like you're not going to decode what you thought you were going to decode. Okay. And so just last slide from today and then we are done. So these are basically, I guess, the main takeaways from today. So ML-based codecs, they allow you for learned encoder-decoder transforms, better fidelity to chosen probability models, right? So that basically gives you the better rate distortion. So this is a point which we spent a significant time today. You can choose whatever distortion you want as long as it's differentiable. Again, very powerful because allows you to just tomorrow, if there is a better vision model, you can make a better compressor for that. Then you can have something domain adaptable and flexible. The main idea to achieve the ML-based things was like just be able to differentiate across this quantization and discrete probability models. And most likely are going to see more and more ML-based codecs in your future compressors. So very hot and active area, participate in it. Cool. That's it. Thank you.